Okay, welcome to the second lecture in Unit 8. This is called Limitless. The quote that we have is from Mark Twain. It says, "Civilization is the limitless multiplication of unnecessary necessities." So the learning goals from this. Students will understand how limiting reactants and excess reactants affect the products of a chemical reaction. Secondly, students will be able to determine which reactant is the limiting and excess reactant. And students will be able to calculate the theoretical yield of products. And so essentially what we're going to use is we're going to start using our stoichiometry and applying it to chemical reactions and what actually takes place in the lab. So what we already know coming into this is that the coefficients of chemical equations show the number of each atom or mole necessary for a reaction. So we see that 1 mole of our sulfuric acid, which is right here, to 2 moles of sodium hydroxide produces 1 mole of our sodium sulfide and 2 moles of water. And so that shows us our mole ratio. What we learned in the lab is that not all reactions have the right mole or the right ratio of molecules or the right mole ratio. So 1 mole of sulfuric acid mixed with 1 mole of sodium hydroxide will not produce 1 mole of sodium sulfide because they're not in the right ratio. And very rarely in the lab do we get specific mole ratios exactly the same. So what this produces is this gives us, in this case, is a limiting reactant. In nearly all reactions you'll run out of one reactant before running out of another. And so we'll run out of something before we run out of something else. And so we have a limiting and we have an excess. So the reaction is limited to the least available reactant. So the limiting reactant limits the amount of product that can be produced, or it limits that reaction. So if 1 mole of hydrogen gas and 1 mole of oxygen are available, then 2 moles of water cannot be formed because we don't have the right mole ratio. We have that limiting reactant. So when we're looking at it, the limiting reactant is not always the one with the greatest coefficient. Okay, in plants, water is generally the limiting reactant because there's a lot of carbon dioxide in the atmosphere. So when we're looking at this, when plants are going through photosynthesis and are producing that glucose, that sugar, water is the key factor here because we don't have enough of it. There's plenty of carbon dioxide go around, but there's not enough water, and so therefore that limits the reactant. So when finding the limiting reactant, what we really look at is we take the number of moles available and divide by the coefficient in the equation. That's the lowest value is the limiting reactant. So the limiting reactant is always the smallest. So when we're looking at this is an example. It says a sample of 10 grams of ammonia is mixed with 20 grams of oxygen. And so when we're looking at this, we first have to get them into moles by dividing by the molar mass because they're both in grams. Remember, anytime we see grams, we have to write the molar mass. And then in one reaction, it requires 4 moles of ammonia. In one reaction, it requires 5 moles of O2. And this will show us how many reactions can take place. Well, with the oxygen, only 0.125 reactions can take place. In ammonia, we can have 0.147. So we can do a greater amount of ammonia. That's not possible. We're limited by the lowest number. So 0.125 reactions can take place because oxygen is the limiting reactant. We don't have enough of that oxygen. So let's look at an example. It says find the limiting reactant if 250 grams of calcium carbonate is reacted with 100 grams of hydrochloric acid as shown below. And so when we're looking at this, here's our calcium carbonate, here is our hydrochloric acid. So when we do this, we go ahead and we start here. Remember, we have to get them to moles because we have to be able to compare apples to apples. We cannot compare anything else. We got to compare it in moles. So first thing we're going to do is we're going to go from grams of hydrochloric acid to moles of hydrochloric acid, and from grams of calcium carbonate to moles of calcium carbonate. And then what we're going to do is we're going to look at, in one reaction, how many moles of HCl are required. Well, 2. In one reaction, how many moles of calcium carbonate required? Well, 1. So we'll go ahead and we'll start by doing hydrochloric acid first. So the first thing we write down is that kind of our mole ratio, that 2 moles of HCl are required for one reaction. And since it said grams, anytime it says grams, what do we have to find? Molar mass. And 1 mole of HCl equals our molar mass of HCl, which is right around, molar mass of HCl is right around 36.45, right around there, because chlorine's 35 and then hydrogen's right around 1, so 36.45 grams of HCl. Okay, then when we look at this, we go ahead and set it up. What do we start with? We always start with what the problem gives us. It gave us 100 grams of hydrochloric acid, so 100 grams of HCl. Set it up. Grams is right there, so guess what goes on the bottom? Grams. Put the other half of that statement of equality on top. And then we look at the reaction. So in 1 mole to cancel out, and then that's in one reaction. So when we're looking at HCl, what we're saying is that HCl is going to produce 1.37 reactions. Okay, that's of HCl. Now we have to do the exact same thing for calcium carbonate. So when we look at this, we go ahead and we look at, in one reaction you have 1 mole. So we kind of write 1 mole of CaCO3 in one reaction. And then we also need the molar mass of it. And so the molar mass of calcium carbonate, 1 mole of CaCO3, when we add all of those up, is going to give us right around 100 grams of CaCO3. Now remember, what do we always start with? We start with what it gives us in the problem. So when we're starting with what it gives us in the problem, we're starting with 250 grams of CaCO3. Set it up, and we see that grams is on top, so grams goes on bottom, and that would be 100 to 1 mole. And then, let me scoot this over, then we keep going, and 1 mole in one reaction. And we see, once we multiply this out, what we see is we'll get 2.5 reactions if we have calcium carbonate. Well, which one's the lowest? The lowest number of reactions is our limiting reactant, so that is our HCl. So that means that HCl is our limiting reactant. So let's go ahead and look at another example. It says find the limiting reactant if 200 grams of octane is combusted in the presence of 500 grams of oxygen. So when we're looking at this, we need to go ahead and have our chemical equation. So let's go ahead, for time's sake, I'll go ahead and write this out for us. Kind of go a little bit quickly here. We've done this one before. It's C8H18 plus, and that's 2 moles of that, plus 25 moles of O2 produces 16 moles of CO2 plus 18 moles of H2O. Okay, there's our balanced chemical equation. Now we're going to have to do this twice, just like we did the previous problem. And we're going to look at our octane, and we're going to look at our oxygen. So let's go ahead and start working these out. Remember, we write it down. It says grams, so what do we need? We need the molar mass of octane. So 1 mole of our CaCO3 C8H18 equals our molar mass of right around 114 grams. And then how many moles in a reaction? 2 moles of C8H18 in one reaction. Okay, we go ahead and we set this up. Start with what it gives us. It gives us 200 grams of octane. So 200 grams of our C8H18. Set it up, and we start plugging everything in. 114 grams in 1 mole, and then we cancel out moles in one reaction. And what we'll get here is we have it'll produce right around 8, or it's not 8, but 0.877 reactions. And then we go ahead and we're going to do the exact same thing for oxygen. So we'll get rid of all this and do the exact same thing for oxygen. Remember that octane produced 0.877 reactions. So when we do oxygen, we know that 1 mole of oxygen is right around 32 grams, and we have 25 moles in one reaction. So when we're doing this, start with what we got, 500 grams, and we go ahead and put our grams on the bottom, moles of oxygen on the top, and then we have, keep going, and we have 25 moles to every one reaction. And what we see here is we go ahead and work this out, and we'll get 0.625 reactions, and that means that oxygen will produce less, so oxygen is the limiting reactant. Now, what does the limiting reactant give us? And this is probably the most important thing here. When you have the limiting reactant can help us calculate the theoretical yield. The theoretical yield is the maximum amount of product that can be produced. It's calculated from the limiting reactant. So every atom of the reactant reacts with another until one runs out. The theoretical yield equals the mass of all atoms reacted. The limiting reactant is what is used up in the chemical reaction. We don't have any of it left once the chemical reaction has taken place. So an example of this is after we find the number of reactions, we can calculate product from that, from the limiting reactant. So I can say that since my oxygen in this example is my limiting reactant, it produces 0.125 reactions. Well, 0.125 reactions, I can then calculate my nitrogen monoxide, and I can calculate the grams of it. This would be my theoretical yield. And theoretical yield will be very important in our next section of this unit. But that's what the limiting reactant does. It can help us calculate that theoretical yield, which is what will be produced. So let's just go straight into an example. It says that a student is responsible for extracting copper from copper sulfate in a recycling plant. The student mixes 50 grams of copper sulfate with 500 grams of zinc in an aqueous solution according to the chemical equation shown below. What is the expected theoretical yield in grams of solid copper to be extracted from the solution? So when we're looking at this, we go ahead and we look at it and we see, hey, it's already balanced. It's a 1-to-1-to-1 ratio. And so we can go ahead. The first thing we have to do is find out what the limiting reactant is. So when we're looking at it, we have 500 grams of zinc, and we have 50 grams of our copper sulfate. And so what we got to do is we got to find out, well, how many reactions are actually produced. What's the limiting reactant? So when we go ahead and we do this, we do need the molar masses. So I'll go ahead and I'll do one of them in purple, and we'll start with the copper sulfate. So when we look at the copper sulfate, what we see is that we know that there is 1 mole in one reaction. So 1 mole of CuSO4 equals 1 reaction. And then we also need the molar mass. So 1 mole of CuSO4 equals the molar mass, which is right around 160 grams of CuSO4. Okay, so we go ahead, we start with what we're given. We're given 50 grams of this, so 50 grams of our copper sulfate. Grams is right here, goes on the bottom, 1 mole goes on the top. Then we keep going with our, because we don't have the reactions yet, so 1 mole in 1 reaction. And what we'll see is that our copper sulfate will produce 0.3125 reactions. Okay, we'll do the same thing for zinc. So we'll take zinc and do the exact same thing. We'll do zinc in blue. So when we're looking at this, we know that 1 mole of zinc in 1 reaction. And we know that 1 mole of zinc is right around 65 grams of zinc. And we start with what we're given. We're given 500 grams of zinc. And we go ahead and we set everything up. We put our grams on the bottom. We put our moles on the top. And then we keep going to figure out how many reactions it'll produce. And then 1 mole to cancel that unit out. And 1 reaction on top. And so we've converted, and we see that our zinc, what we'll have is 7.69 reactions can take place with zinc. 7.69 reactions. So what's the limiting reactant? Well, that's going to be copper sulfate, which that should make sense because there's a 1-to-1 ratio, and their masses aren't incredibly different. I mean, it's 100 grams, but when we're looking at this 500 to 50, it's a multiple of 10, and so makes sense that the copper sulfate would be the limiting reactant. Now it says, when we're doing this, it wants to know what is the expected theoretical yield. So what I'll do is I'll take my reaction here. My 0.3125 reactions can take place, and I want to know how much copper. So in a reaction, I have 1 mole of copper. So 1 reaction equals 1 mole of copper. And it wants to know grams, so I know 1 mole of copper is right around 63.5 grams of copper. Okay, why did I need that? 'Cause it said grams of copper. Anytime it says grams, gotta have the molar mass. So I set this up, and when I see 1 reaction, that'll cancel out there. It's 1 mole of copper, and then we keep going. 1 mole of copper is our 63.5 grams of copper. And what we'll see is that we can produce a theoretical yield of 19.84 grams of copper. And that would be our answer.